Hi, I'm Mike Stanzik and welcome to Digital Electronics Classroom. Today we're going to be looking at Boolean expressions and how we can simplify them. In previous videos we looked at how we can generate the min-term and max-term expressions from a truth table, but those are unsimplified, and so we want to optimize these expressions. And so I'm going to show you some of the properties of Boolean math and Boolean algebra that we're going to use. Now, I'm not going to do an exhaustive look at all of the properties of Boolean algebra. Instead, I'm going to pick some of the ones that I think are most valuable for most of the simplification that you will be doing. And if you're interested in more detail, I would recommend looking in a textbook or looking online to get some of that. So I'll try to embed some of that as it comes along, but that is not my focus here. Okay? All right, this is part one. Let's get started. So we're doing, oops, make sure we get our pen selected, Boolean simplification. Awesome. So when we simplify, we are optimizing. And in the real world, optimization is going to take place for an economic purpose, to make our solutions simpler and so that when we manufacture them, they cost less. And so basically, we want to reduce the number of gates that we need to use to implement our solution, and we also want to then reduce the number of inputs to those gates. And so to make that happen, we're going to reduce the terms. We're going to have the fewest terms in our expression, and then we want the fewest literals inside those terms, in that order. So we want fewest terms, and then fewest literals. Typically, this is the approach. So let's do an example. So I'm just going to kind of show you what this might look like. So if we had an expression that looked like x, y, z bar, or x, y, z, or x, y bar, z bar, or x, y bar, z. Right here you can see we have 4 terms, and each of the terms has 3 literals. Now, I'm not going to show you how I get here, but this is another expression that does exactly the same thing. And so we have xy, or xyz bar, or xy bar z. All right, so this does exactly the same thing as the previous one, but in this case, you can see we have fewer gates and fewer literals. And then let's go a little bit further. We have xy, or xy bar, and then finally we have just x. And so although this min-term expression up here is valid, as we move to smaller and smaller expressions, we get a better and better optimization. And so that's what we're looking to do here when we're doing our optimizations and doing our simplifications. So I'm going to try to introduce the kind of main techniques, the main properties of Boolean algebra that I think you'll use to start to do your simplification. And so distribution, complementation are 2 of them that I think you will use right off the bat. So I'll introduce those as we kind of go along. But distribution is very similar to normal algebra distribution, and so I think you'll feel pretty confident with that as we look at it. So let's just introduce those. Distribution looks like this, and so there's 2 forms. There's an AND form and an OR form for all of these properties, and those are called duals of each other. And so we're going to look at one particular form for each one because I'm going to use the one that I think is going to be most valuable for you. And so in this case, we're going to look at the AND form, so you might have something like this: x and y or z. And that's going to be equivalent to x and y or x and z. And so we distributed the x into both the y and into the z. Okay? And so it looks like a product, and that's what we're kind of remembering from basic algebra, but in this case it's an and, right? And so if you notice, we're going from this situation, which looks more like a min-term situation, and actually we're going to probably do this from right to left in most of our simplification procedures, so just so you're aware. Complementation. And in this case, we're going to look at the or form of this. So if I have something that is like x or x bar, so these are the same literal, but one is complemented and one is not. And so x or x bar is all cases. So if you have x, then this one will be true, and in an or, that makes the whole function true. And if you have an x that's a 0, then this one will be a 1, and then the whole function will be 1 because of that or. And so this turns into a 1. It's just true, okay? So that's what we call complementation. So let's get started with an example. Of how you might use these two together. So what if you were given this expression? F is x, y, z bar. Oops, sorry. There's another form of making a complement, and that's an apostrophe. You typically would use that if you're typing it out, word processing it, if you will. And so when I'm drawing it, I like to use the bar because I think it's a little easier to see. So this is a pretty simple example. We have x, y, z bar and x, y, z. Notice that the three inputs that we have for this system are x, y, and z, and that all of them are in each of these terms. So this defines this expression as a min-term expression. So what are we going to try to do here? Well, we're going to try to eliminate some of these literals and reduce terms if we can. Right away I can see that there's an xy in both of these terms, right? And then z bar is there and z is in the other one. This is something that indicates to me that we can do a distribution. So we're going to go into the opposite direction as the definition. But we're going to pull an xy out, and we're going to be left with z bar or z. And then this step was distribution. Okay. And the next step here is to look at z bar or z, and we saw that that's a complementation. So z bar or z is a 1. That's complementation. And then there's actually one last step here which I didn't define for us yet, and that is one ANDed with anything. And so if you already have a 1 there in that spot, you don't have to worry about that 1. That 1 is true for an AND. And so you can leave that 1 alone and get rid of it and just look to see if x and y are both true. And so if x and y are true, then the whole expression is true. We don't have to worry about that 1. And so this turns into xy. And that property is called, it's called identity. So that's the identity property. So one ANDed with something is just that something. That's the identity property. So that's our approach here. If we look at two terms and we see that everything is the same except for one of the literals, then we can pull out that everything, distribute it, and then we get the two literals that are opposite from each other. They are complements. And then that turns into a 1, and we can use identity to get our final expression. And you can see that that expression has only one gate, and that's a more simple expression. It is optimized. Let's do a second example. So in this example, we're going to have x, y, z, or x bar, y bar, z, or x, y bar, z. All right, so where do I go from here? Now we have three terms, and we're trying to find two terms that have like literals, except for one that is different. And when I look at x, y, z, and then I look at the next one, z is the same, and I could distribute the z out if I wanted to, and then I'd be left with x, y, and x bar, y bar. But let's look if we can see if we can find everything the same except for one literal. And let's look at these next two. X bar, y bar, z, x, y bar, z. Y bar is the same, and z is the same, so I could take those two and distribute them. And let's look at the first and the third. Excuse me, x, y, z, and then x, y bar, z. And so in this case, y bar is different. So I could choose the second and the third, or I can choose the first and the third and do a distribution to eliminate one of the literals. And so let's just choose the first and the third. So I'm going to take x and z out, and we got y or y bar. And then we still have this x bar, y bar, z that remains. And so this is a step of distribution. And then y or y bar becomes x, z, 1. And this is a complementation. And then we have x, z. And this is identity. And then let's see, where can we go from here? It looks like we could do a distribution with z. So I could go z, x, or x bar, y bar. And that would get me to there. But the question is that better than the one above it? And you can argue one way or the other depending on what you're trying to do. But I'm just going to leave it in this form right here and say we did a good job of eliminating one term and then eliminating one literal from one of the other terms, and we have a reduced expression. Now some of you will be looking at that and say, hey, Mr. Stancic, you can reduce that further. And you are correct, we can reduce that further, but we don't have the tools to do that just yet. So I'm just using distribution and complementation, and so we're going to leave it here, but even this is reduced from the first expression that we had. So that's all we have for this episode, this video. I hope you found that valuable, and my advice to you is when you're looking at a min-term expression, which is usually the first place that we will start when we are doing our simplification, that you're going to want to look for pairs that you can distribute and then use complementation to reduce, to remove a literal from those expressions, okay? So that would be my advice to you. I'm Mike Stancic, this is Digital Electronics Classroom. Make sure you like and subscribe on the videos, and have a nice day.